Good morning, everyone. This week we have two young speakers about their up-and-coming work, and starting with Noga Alon, all the way from Princeton University.
Right. Thanks. Always a pleasure to be here. Thank you all for coming. So I talked about this extended notion of VC dimension. That I think is interesting, and the motivation is some problem in discrete geometry. It is a joint work with Shakhar Smorodinsky and from Ben-Gurion University, I guess. Let me start with some preliminary comment. Incidentally, of course, feel free to ask me whenever you have any questions about anything. Here is a preliminary comment. So this has to do with the choice of the subject. I apologize to Maya, we've seen it, maybe. And it has to do with a choice of subject, and has to do also with the increasing role of AI tools in our life. So this is something that recently, a message that I got from something called Scholar GPS. It's one of these analytics companies, that they do statistics about citations, publications, and impact. And they tell me that I'm listed number 2 in the category of food coloring. And actually have here an illustration. So this is food coloring, and I was a little bit surprised. So I looked.
I'm sure the number 2 immediately.
So indeed, it's I'm like the second. So second in food coloring, and actually knows the first one and also the third one. And in fact, we have a joint paper, all three of us, and written some time ago, maybe 20 years ago, and it uses VC, the theory of VC dimension. So I thought, I don't have any recent results in food coloring, but I thought that's a good opportunity to choose something that is related to VC dimension, and so here is indeed the title again. And here now you see also a picture of Shakhar, and here really so he prepared the initial slides, gave a lecture on this, but and it was too tempting, so that's why I'm not using the blackboard, but I modified them quite a bit. Okay, so let me tell you what I'm talking about, and in the beginning are things that you all know very well, that are completely standard and trivial about convexity, but still I'll go over it just to set the notation and to agree about what we are talking about, and to show you some of the animation that Shakhar prepared. So we'll talk about the d-dimensional Euclidean space, RD. Although at the very end, maybe I'll mention something about abstract convexity spaces, but mostly I'll talk about the usual Euclidean space. And the set is convex if for any 2 points, like you see here, it contains also all the line segment joining them, as you all know. And it's important that the intersection of convex sets is also convex, it's also standard and trivial. And if we have any set, finite or infinite in RD, which is not necessarily convex, then we can define the convex hull. The convex hull is just the smallest convex set containing P, or formally the intersection of all convex sets containing P. So, so this is of course a convex set, and some picture here also. So here is a convex hull. You see that some points are in the boundary, but some points are also inside. And of course, the convex hull is convex, is closed under convex combinations. And if the set that we started with is finite, P1 up to Pn, then the convex hull is just the set of all convex combinations, namely all linear combinations with non-negative coefficients whose sum is 1. So this is about convexity and about the convex hull. So a basic theorem in convexity was proved by Johann Radon in 1921. And what it says is that any set of d plus 2 points in RD, you can partition it into two disjoint sets so that the convex hulls intersect. And d plus 2 is tight because if we have d1 points in convex in general position, for example, 0 and the unit vectors, then it's easy to see that there is no such partition. The motivation of Radon was to give a proof of an even more fundamental earlier result in convexity, the theorem of Helly, another Austrian mathematician. And indeed, now the standard proof is the one that is based on Radon's theorem. Helly theorem is from 1913, but he actually published the proof only later, even after this paper of Radon, and after another proof by Koenig. But okay, so this is Radon's theorem. It's a basic theorem. It's pretty simple to prove it. So it's some simple linear algebra. I'll not show it. Feel free to ask questions if you want. It's easy to show it. It's 3 lines. Okay. Okay, and here is an example. So whenever we have 4 points in the plane, right, dimension 2, then we can partition them into here it's the red set and the blue set, and you see that the convex hulls intersect. And the other combinatorial possibility of 4 points in the plane is 3 points and 1 in the convex hull of them, and then it's also clear what is a partition. Okay, but the same holds for any dimension. So this is Radon's theorem. It has, and I wrote here an equivalent statement, and somehow it will be better maybe to think about it like this, but it's trivially equivalent. So whenever we have d plus 2 points, we have a partition into 2 disjoint sets, so that A and B, so that any convex set containing A must intersect any convex set containing B. It's clear that this is the same. Now, there are lots of extensions and invariants of Radon's theorem, and maybe one of the nicest is by Helge Tverberg in the 60s. And this already not so simple, but is a very nice theorem. So it says the following, that if we have a set of R minus 1, so R now is at least 2, the case R equals 2 will be a Radon theorem. If we have a set of R minus 1 times D plus 1 plus 1 points in RD, then we can partition the set of points into R pairwise disjoint sets, so that convex hulls, all of them intersect. There is a point that belongs to the convex hull of each of the sets. So the case R equals 2 is Radon theorem, and this one is also tight. So for example, if you take again the vertices of a simplex, and you take each one r minus 1 times, or if you want them to be distinct, just next to near every point of simplex, put r minus 1 points, then, so this is r minus 1 times t plus 1 points without the plus 1, and you cannot partition them to r sets that have that the convex hull all intersect, because one of the sets will miss one of the vertices of the simplex. You can convince yourself. So, so this is, and this by now has several proofs, but none of them is really simple. Yeah, it's not safe. Okay, and here is a picture, right? So, so you have here a 7 points in R2. And therefore, we should be able to partition them into 3 sets so that the convex hulls intersect. And you see that the red set and the blue set and the green set have a common intersection of all the convex hulls. Good. So this is Radon, Tverberg, and now let me mention a problem of Kalai. Again, here I wrote this equivalent formulation. So, so whenever we have R convex sets and AI is contained in CI, then the CI must intersect. Okay, here is a problem. Suggested by Kalai in the late 70s. And so I want to call a set in RD S-convex is the union of S-convex sets. And the S-convex sets are not necessarily disjoint, so it gives you more freedom if you are allowed to choose not necessarily disjoint convex sets. And this is an S-convex set. So one convex will just be convex, but S-convex is more general. And then here is the problem that Gil suggested. So we want to get good bounds for this smallest number f, which is a function of the dimension d and the parameter s, so that whenever we have f of ds points in Rd, we can partition them into 2 disjoint sets, so that whenever you have an S-convex set containing A, it must intersect every S-convex set containing B. Right? So the S equals 1 case is a case of Radon's theorem. Yeah, this is what is written here. So in Radon theorem, we know exactly what is this value. And Gil knew, and actually it's maybe the best place to find it is in a more recent paper, a survey paper by Imre Baran and Gil Kalai, is that this f of ds exists. It's a finite number, but the proof they have is a kind of simple proof. It's based on a Ramsey theorem for hypergraphs to get that when you have enough points, then you get many of them that lie on the moment curve or have the same combinatorial type as points that lie on the moment curve. And on the moment curve, it's kind of easy to understand what is happening. But because you use hypergraph Ramsey, then the bound that you get is bad. So is some tower of height, maybe some function of this S. And the feeling was that the actual truth is much smaller. So we want to understand this. And this would be the first thing, because I talk about it, at least in the first half of the talk, I want to have this here. So just the definition. So we said that f of ds is a minimum F, so that for every set P in R D, and the P is at least or exactly F, there is a partition. The partition of P is into disjoint sets A and B, so that for every s-convex sets C1, C2, that contain A and B respectively, we have that s-convex sets intersect. So this is one quantity we will consider. And what I'll show you, at least in the first half, is a pretty simple proof that that will give that that this f of ds is at most ds squared up to some logarithmic factor. And this is nearly tight, so we don't know a very completely exact bound, but this at least is tight up to the logarithmic factor by a more recent construction by Chen, Ge, Shu, Wang, and Shu, which gives a lower bound of constant ds squared. So up to the logarithm, this is tight. Okay. Good. So any questions about any of these? Because what I want to do is to maybe first tell you about the connection between VC dimension and the original Radon, and then show that the same type of connection would give a pretty simple proof of this. And then I'll talk about generalization of Tverberg, which is more complicated and also leads to this extended notion of VC dimension.
Is there any reasonable off-diagonal question? Like, can you ask every s-convex set contained A must intersect every t-convex set?
Sure, right, yeah. So actually, I just wanted that it would look simple, but the same proof and the same results, all for off-diagonal. So you may want to ask that every s-convex set that contains A intersects every t-convex set that contains A. And then instead of the s square, you will have s times t. So it will be, so it really, and the log will be, let's say, of the product or the sum. Any other? Good. So let me also, so let me describe this connection to this dimension. And at the beginning, I just want to show you that Radon's theorem is just equivalent to some statement about the VC dimension of an appropriate family. The only things that you have to be, so this will be very simple, the only thing that you have to be a little bit careful about is that the VC dimension, well, I didn't define it, I also define it, probably many of you have seen it before. The VC dimension of the set of all convex sets, even in the plane, is infinity, actually. So we have to look at the VC dimension of something else. Okay, so what is the VC dimension of a hypergraph H? And as I said, probably many of you have seen it, but I'm not going to assume it. So we say that a subset S of vertices is shattered by the hypergraph if every subset of it is obtained by the intersection of the original subset with an edge. Namely, if we look at the intersections of the edges of the hypergraph with this specific set, then we get all possibilities, all the 2 to the s possibilities. Okay, so this is shattered. And then the VC dimension that I denote here by dim of H of a hypergraph H, it's just I wrote here supremum because maybe it's infinity, but in the cases that we will be interested in, it will be finite. So it's the maximum size of a shattered set. Okay? So this is the vici dimension of the hypergraph. The hypergraph may be infinite, right? In many of the geometric examples, it will be infinite. And this notion of vici dimension has lots of applications. So machine learning, actually in PAC learning, the basic theorem is that a family of functions is learnable, whatever this means, in the PAC model, if and only if the vici dimension is finite. It appears in discrete geometry. We'll see one example now. It appears in probability, in combinatorics, social choice, in model theory. Well, I couldn't be in the lectures of Marianne last week, but I would guess that she mentioned vici dimension, little stone dimension, and some. So it's really.
She also mentioned the recent work of hers on a variant on vici dimensions for convex set in the plane that, by restriction to axis parallel lines.
I see. So
lower from infinite to finite. Yes, Corleone.
Okay. I see. Yeah. So
Maybe you know.
Right. So I don't know all of them, but yeah, maybe I should have come. But okay. But good. So so indeed, vici dimension and extensions and variants appear a lot. And indeed, when we look at vici dimension of okay. So there are many. Okay. So here is an example. Examples that is relevant to geometry. Suppose it's a hypergraph. The set of vertices are all the points in the Euclidean plane. You can look at higher dimension also. And the set of edges are all the half planes. So just all the half planes. Then the dimension is 3. Okay, why is the dimension 3? Because if you take 3 points in general position, then you can separate them, or for every subset of these 3 points, like one here, you have a half plane. So you should think about this thing as a full half plane that contains exactly these 2. Right? And the same for every other subset. And on the other hand, if you have, so here is also an example of a red point that contains this one. And of course, you can separate them in any way you wish by a half plane. And if you have 4 points, then in fact, exactly because of Radon theorem, but let's just look at this example. So you cannot have a half plane that contains the middle point here without containing any of the 3 other points, right? So these 4 points are not shattered by half planes. And also for the same reason, or for a similar reason, these 4 points are not shattered by a half plane, because any half plane containing these 2 points will contain either these or these. So we cannot have them. Okay, so the vici dimension of this hypergraph is exactly 3. And we want to observe that really the vici dimension and the Radon partitions are the same thing. And I wrote it here just for half planes, but this would work in general. So I am claiming that the Radon number is at most d plus 2 in dimension d, in the same Radon numbers that we mentioned when mentioning Radon theorem. This is equivalent to saying that the vici dimension of half spaces in dimension d is at most d plus 1. And let's just see it. It's just a definition, but I'll still go over it. So if you have a Radon partition of a set S, AB is a Radon partition, then it means that there is no half space that contains A and does not contain any point of B, because then this half space separates them, so the convex halves cannot intersect, right? So that shows an inequality in one direction, and I say it in this way so that I'll not have to think in which direction. One direction. And on the other direction is that if S is not shattered, the set is not shattered, then it means that there is some subset A that there is no edge, namely half space, that contains exactly this A and does not contain B. That means that A and B cannot be separated by a half plane, and it's okay. And I told you before that the VC dimension of the set of all convex sets is infinite, but here's the additional easy argument is that that we replace the convex sets by half planes or half spaces. This is okay. So this is essentially the same statement to know a Radon type theorem and to know something about the VC dimension, and this suggests that that something similar could work maybe for extending this to the version that was asked by Kalai. But before doing this, let me mention this lemma. So this is a basic combinatorial lemma in the theory of range spaces with bounded VC dimension. And this was proved many times by lots of authors, so specifically by Sauer, by Perles-Shelah, actually also by Svorodenskis, although they proved it not with a precise bound, but something similar. And like many results of this type, it was conjectured, the exact statement was conjectured by Erdős. And as I said, it was proved and reproved again by many people, but Perles is the only one who proved it twice, kind of independently. So he really forgot his first proof and proved it again. This is a true story, but anyway, so and his second proof is different from his first proof. There are many proofs. All of them are pretty simple, but they are really different from each other.
And he didn't teach you this.
That what?
Perles was his advisor.
Yes.
That you would also have two papers.
Yeah.
Or three.
So, yeah. So, okay, so what does this say? This statement, we have a hypergraph, VE, and suppose that the VC dimension is D, is bounded, is finite. And then we can look at any subset of M vertices, and we intersect all the edges with this subset. So we look at all the projections. These are all the, and we ask how many distinct ones we have. Okay? So I could have, instead of everything that is written here, I could have said that we have a hypergraph with M vertices and VC dimension D. How many edges it can have? This is equivalent, because when you take the projections, the VC dimension cannot increase, but still it's better to formulate it in this way. And this gives a tight bound. So the maximum number of such projections we can have on a set of size M is the cardinality or the number of all sets of size at most D. The example, or one example, is just to take all the sets of size at most D, and this has VC dimension D, because to shatter a set of size D plus 1, you need some edge of size D plus 1. So this is tight, and you see that it's quite interesting, right? So it says that you have this, say, infinite hypergraph, then we can look at this function. So this function is well-defined function. You're allowed to choose M vertices, and you ask how many distinct projections you have on it. And what this lemma tells us, that the behavior of this function, well, either there are infinitely many sets that are infinitely many growing, infinitely many cardinalities of sets that are shattered, and then this function is 2 to the n, is the biggest that it can be, right? And what is written here is that if it is not 2 to the n, it grows only polynomially. So it cannot be, there is some dichotomy, I think. It cannot be a function that looks like 2 to the square root, for example. If it's not exponential, then it's polynomial. So this is somehow useful. Okay. So now let's go back to this problem of Kalai. So this function that is written here, f of ds, and we try to bound it. So we want to show that it is not more than some constant ds square up to some logarithmic factor. Okay? So, and we try to follow the same argument that shows that Radon and VC dimension is kind of the same. So we would need two lemmas, and both of them are pretty simple. So we can one by one. So here I'll try to show you everything. Okay. So the first is that if we have two disjoint s-convex sets in Rd, so we have two sets in Rd, they can be covered by s-convex sets, or each of them is a union of s-convex sets, and they are disjoint, okay? Then we can find convex polytopes, say K1 up to Ks, so s-convex polytopes. Each of them has at most s facets, so it's not too complicated. And the first set is contained in the union, and the second set is disjoint from the union. So we can kind of separate these two s-convex sets using the union of s polytopes, and each of them has at most s facets.
They replace half spaces by the intersection of s half spaces.
Right. So you're saying if you compare to Radon, then you replace half spaces, maybe I would say, by the union of intersections of S. The union of S things, each of them being an intersection of S. Of S.
Yeah, I mean each one of the polytopes is an
right.
intersection.
Yeah. So each one is
Could the polytopes be infinite?
So this would be the first lemma.
Could the polytopes be infinite? Like, should I think of the half space as a polytope?
Yeah, so I allow it to be unbounded. It doesn't really matter much. Okay. So let's indeed agree that for me a polytope is also in unbounded. So just the intersection, by definition, it's the intersection of S half spaces. So this is okay. So this is the first lemma that we will prove. It's a simple lemma. And what is the second lemma? It's also pretty simple, and it says the following: that if we define now the following hypergraph, which is natural to define in view of lemma 1. So the set of vertices are all the points in the d-dimensional space, and the set of edges is a so I call a set A is should have really written okay. So just the union of S polytopes, each having at most S facets. So these are the edges. We take all the possibilities of unions of S polytopes, possibly unbounded, each of them being at most being the intersection of most S half spaces. So these are the edges. It's what we said before, that we replace the half spaces by these unions of intersections. And then the claim is that the VC dimension of this thing is also not too big. So it's just some constant, maybe 2, 3, I don't know, ds squared times the log of S plus 1. This is part of, it's part of some general statement of what happens to the VC dimension when we apply some Boolean operations. Okay, so these are the two lemmas. And let me just show you that the two lemmas, so I want to really describe the proof of these two lemmas, but maybe I'll first show you why these two lemmas imply the bound for this FDS. So we will just kind of imitate the same proof that we said for Radon. So we have this H that is written here, the hypergraph, that the edges are unions of S polytopes, each having at most S facets, and let n be its dimension. And I want to say that this f of the S is at most n plus 1. Right? And that gives a bound, because if we believe lemma 2, and this is why, so it's again as before. So you take a set P with n plus 1 points, okay? And this set P is not shattered by H, because the VC dimension is only n, and we took n plus 1. So if it is not shattered, then it means that there exists some set A, so that whenever there is an edge of this hypergraph that contains A, then the intersection of this edge with the set P cannot be exactly A. And then the claim is that the partition of P into A and the complement of A is the required partition. Let's just check it. So if not, then it's not the partition as we want. Then there are C1 and C2 that are two S-convex sets in RD, so that A is in C1 and B is in C2, and the two sets do not intersect. But now, because of lemma 1, there exists exactly a union of S polytopes, each having at most S faces, namely there exists an edge of my hypergraph that contains C1 and is disjoint from C2. But then it means that exactly this edge, the intersection of it with P, is exactly A, because it does not contain anything from B. It does not even contain anything from C2 that contains B. Right? So this is the required partition, and that's it. Right? So we just need the two lemmas. Any question about this? It just this is the general connection between the VC dimension and the existence of some sort of Radon type partition. So we have to prove the two lemmas, and for this one, the two lemmas are also simple. I wrote here the proofs. So here is the first lemma, that we have two disjoint S-convex sets, and we want to separate them by this convex polytope. So it's like that for S equals 1, when we have two disjoint sets, then we can separate them by a hyperplane, and we do it's obvious here. So we have this union of S, not necessarily Perberg disjoint convex sets x1 up to xs, and we have this C2, which is a union of S other convex sets. And then we know that we can separate each xi from each yj, because these are disjoint convex sets. We assume that there is no intersection. So for every xi and every yj, there exists a half space hij that contains xi and is disjoint from yj. Okay? And that means that if we look at the intersection of all the hij as j varies and I is fixed, so all the half spaces that contain one of these convex sets, xi, and is disjoint from one of the other yj, if we look at the intersection of them, it still contains xi, but now the intersection is disjoint from all the yj's, right? And this intersection is a convex polytope, possibly unbounded, but it has at most S facets, right? It's the intersection of S. And now just the union of all of them is contained in the union of the Ki, and C2, the union of the Yi's, is disjoint from this union of the polytopes, because each of them was okay. So this is basically the first level. Okay. And what is the second? The second is also simple, and as I said, it's some special case of something more general and in fact standard about range spaces with a finite VC dimension. And it's just that if we start from any hypergraph, I guess that here this should have been H prime here, but never mind. So we start from any hypergraph with VC dimension D, and now we apply, we have any Boolean function of k variables. So we can use unions and intersections and differences, whatever you want, with variables x1 up to xk. And now we substitute them, it's written here, we define this second hypergraph H double prime, where the set of edges are, we take in all the possibilities k edges of the first hypergraph, and we apply to it the function. So we get some edge, so we have now more edges, but we don't have so many. So the claim is that still the VC dimension cannot increase too much, namely it's not more than d times the dimension of the dimension of the original 1 times k log of k, basically. And this is from this Sauer-Perles-Shelah lemma, because you can look at the Shakhar function. So imagine, suppose that some set is shattered now, it's a new hypergraph. So you have a set of some size, and every subset of it is supposed to be obtained as the intersection of an edge in this set. And the question is how many intersections you can have. So the possible number of intersections of the original edges with this set is bounded by this Sauer-Perles-Shelah lemma. And now we just are allowed to take any k of them and apply to them the function f. So the number of possibilities is not more than the number of possibilities we had initially raised to the power k. But this has to be at least 2 raised to the power of the cardinality of this set. And if we just work out the arithmetic, then it gives us an upper bound for the dimension.
It's possible that this is not tight. It's possible that it's all of dk.
No, so there are in this generality it's definitely right. So there are examples, but it's true that in each specific or in some specific cases, it may be that we can improve something. So depending on the functions and depending on and it could be that in the geometric application, maybe the loop is not needed. We don't. Okay. Good. So this is very simple, and now I want to tell you something about what is maybe less simple, but still kind of following the same reasoning. So we want to extend Tverberg.
Maybe before just a question. So if you go back to the 2 lemmas, the second one, you basically allowed any combination and any number of alternations between intersection and
right.
So for the first, the s-convex definition of Kalai, it was just union.
That's right.
But you could generalize it also in this way, right?
Right. So actually, someone asked me, I gave this lecture once before, and someone asked me, and it turned out that you can give. So I thought first that it's a very good question. So it's a very good question, but then I realized I thought about it a bit. So you can give very simple examples where it completely fails if you apply. So if you apply differences, then nothing holds for the geometric function. So not because of this lemma, but because of because of the first lemma, that we separate. Because as we said, it's not that the dimension of the set of all convex sets, the VC dimension is infinite. So if you apply to convex sets, general Boolean things and terrible things may happen. So what helped us here is that when 2 convex sets are separated, you can go to half spaces. And if the Boolean functions that you look at is different, then there is no analog to this, and then it will fail miserably. So still, it might be that for some functions there would be, but I couldn't think. I thought a little bit. Okay, I couldn't think about other interesting
What
examples.
class of functions would actually make it?
Yeah, so it would have to satisfy something for this function. But indeed, this lemma indeed works with generalizing about the situation. Okay, any other? Good. So we want now to extend the Tverberg. Tverberg is more complicated than Radon, and maybe therefore it's also not surprising that it will be more complicated to extend it now to the case of s-convex sets, and again it can be done for off-diagonal also if you care, but I'll write it just for s. So here is the question that we would ask here. Is what is the smallest possible integer now? So now there is another parameter r, the number of parts in Tverberg, and d and s. And again, we could have done with s1, s2 up to sr, but let's not worry about that. So that whenever you have a set p of f points, many points in Rd, then you can partition it to r pairwise adjoint sets, so that whenever you have a family of R s-convex sets, where the I set Ci contains Ai, then there is a common point that belongs to all of them. So again, the case S equals 1 is Tverberg theorem. And the question is if we can get some good bound here too. And here the statement is the following. So the bound that we get for this Fr or Ts is not constant, dr square log r s to the r times another log of s to the r. And again, I mean, it looks pretty big, especially maybe because of this term s to the r here. But again, this term is sort of needed. So again, in that paper by Chen et al., they show that at least when d is big, is a function of r, so d at least 2r minus 2, then there is a lower bound of d or d minus a little bit times s to the r. So there are all kinds of logarithmic functions and some others that maybe are not tight, but kind of maybe the biggest or the fastest growing term indeed you need. And we want to try to apply the same kind of proof, and it's and of course, I thought initially that I would have more time here, but it's okay. We will
take your time.
Yeah, but it's okay, right? So we want to apply the same kind of reasoning, but indeed the main thing we need is this. I wrote here key tool is to extend the notion of physical dimension to what may be called R physical dimension. This is some interesting maybe notion of dimension, and maybe it would not be the most natural one you'd think about without the geometric application, but in the geometry it appears naturally. And here is the definition. So again, we have a hypergraph. I want to say what it means for a set to be R shattered now. So the case R equals 2 will correspond to usual physical dimension, although we'll need to think maybe a half a minute to see that indeed R equals 2 is usual physical dimension, but let's not worry about it now. So here is the definition of being R shattered. Whenever you look at S and you partition it in any way you wish to R pairwise adjoint sets, then you need to get R edges so that the SI is contained in EI, right? But I didn't say that the intersection of EI with S is exactly SI. Just said that SI is contained in EI. Maybe EI contains other points of S. But the important thing is that all the EIs together, if you intersect them with S, this will be empty. And so we have so for every partition, I have edges that contain the ith edge contains the ith part, and also all these edges do not have a common intersection in the set. So you can convey, I think I didn't write it here. Okay, and of course the RVC dimension is a maximum or supremum cardinality of an R shattered set. Now I didn't write it here, but in the case R equals 2 correspond to usual VC dimension, because you see R equals 2 means that whenever you partition the set into two sets, there would be an edge containing this part and an edge containing this part, and they are not allowed to intersect inside this set. So it means that each of them indeed contains only exactly the part it has to contain, because if it will contain more, they will intersect inside it. So the case R equals 2 correspond to the usual VC dimension, and R bigger corresponds to something else. And note also that if a set is shattered in the usual sense, for the usual VC dimension, it is also R shattered, right? Because then for any partition of it, I have, in fact, edges that intersect in exactly the part that I need. And then, of course, they will not have any intersection inside, but the RVC dimension may be much bigger, maybe, of the original VC dimension. Okay. And then it turns out that there are again two, or just the way it's written here, there are two lemmas that kind of correspond roughly to what we had before. And both of them are more complicated, but somehow can be done. So this is So the first one is that I just said that the RVC dimension of a hypergraph can be bigger than the VC dimension, but not by much. Sense. So if the VC dimension is D, then the RVC dimension is not more than dr squared log R. Again, this is essentially tight, and again, we don't know about the log. So up to the log, it's tight. Okay. So the RVC dimension may be somewhat significantly bigger than the VC dimension if R is big, but not arbitrarily big. So this is the first lemma. And then the second lemma, which corresponds to the geometric thing, it's also more complicated, but not terrible, that if we have R sets C1 up to CR and CI is s-convex, and the intersection of all of them is empty, so there is no one belongs to a, then we can find sets Ki. Each of them is a union of s-convex polytopes, where each of the polytopes now has at most s to the r minus 1 first. So we have some control, but in these polytopes, the ith polytope contains the ith set, and the intersection of them. So this is a geometric thing, and this is so what I planned to do is, so I looked through this fourth lemma. You have to think a little bit about it, even in the case that S is yeah, okay.
Basically, it's an algorithm for shattering any.
You mean the algorithm for finding this thing? So yeah, you
basically gave us an algorithm for.
You just need to be able to separate a convex set from another convex set. If I have an oracle that gives me a separating hyperplane whenever I have two disjoint convex sets, then I can do it here. So this is it's not. But what I wanted is to show, maybe I wrote it here, that lemma 3 and lemma 4 imply the theorem sort of in the same, or almost in the same way that we described before, you have to think about it a little bit, but basically it would. I mean, if you look at, so I didn't plan to show this, but if somewhere in the proof here, you will see why, you can see why the definition of this RVC dimension is what it is. So somehow this is what will give us what we need for this Tverberg type result. And we would basically use this lemma to define the corresponding hypergraph. Then because of the general previous lemma about applying a Boolean function to something whose bounded VC dimension, we would get a bound for the VC dimension of these. And because of this lemma, we would get a bound to the R VC dimension of these. And then we take one more, so the R VC dimension of these, and this would have exactly this partition that you cannot realize because the set of size, this R VC dimension plus one, cannot be R shattered. This will be the partition that you need. So kind of the general pattern of the proof would be the same. Each step is somewhat more complicated, but not terribly complicated. And the only thing I still wanted to show is maybe this proof of lemma 3, because this is pretty simple. Okay, let me thought that, okay. So suppose that we have this hypergraph with dimension d, and R is bigger than 2, because otherwise it's the same definition as the usual VC dimension, and we want to bound the R VC dimension. So the only thing is pretty simple. So once the claim is that if F is such a number that satisfies the inequality that you see here, then F is an upper bound for the RVC dimension, or indeed even F minus 1. So no set of F vertices is R shattered. So if whenever the sum as I goes from 0 to d of F choose I raised to the power R is less than R over R minus 1 to the F, then no set of F vertices is R shattered, and then you can work out the computation. Maybe I wrote it here, and this will give that F is not more than dr squared log R. Right? So this is basically what we want, and the proof of this is simple. So it's written here. So suppose you have a set S with so it's simple, but nothing looks simple in the end of a 1 hour lecture, but it is. So suppose you have a set S that is R shattered and it has F vertices. I want to show that F is not so big. Okay, so that means because the VC dimension is D, then by this Sauer-Perles-Shelah lemma, the number of, let's say, ordered R tuples of hyper edges in this projection of the hypergraph of the set S, the number of them is just this bound that you get from this lemma raised to the power R, because we have to choose R of them, let's say, in an ordered way. Now, the important thing is that, so you see, you have these R possible intersections, they are not disjoint. And therefore, each of them, each such R tuple can be used for many R tuples, actually, because we just have to choose some partition into R parts so that the ith edge contains the ith part, but some vertices belong to many edges. So you can decide to which part you want to put them. But the important thing is that any point belongs to at most R minus 1 of the edges, because the edges do not have a non-empty intersection inside it. So you have only R minus 1 choices for each point to which part of the partition you want to assign. And therefore, the bounds that you will get for the total number of partitions into R parts that are kind of witnessed by this set of R edges is not more than this raised to the power R times R minus 1 to Z. But this altogether has to be bigger than R to Z. So maybe this is right. So if it is R shattered, we altogether have to get R to Z. So if it is shattered, then this has to be bigger than R to Z, and it will contradict the inequalities that we get here. This one is just a simple counting argument, and in a way it's somewhat simpler to the way that you show that the VC dimension does not increase much when you apply a general Boolean function, but you need this. The main thing here is to define the right definition of this R VC dimension, and that would come in the proof. Let me say that the proofs are combinatorial, and therefore they work for abstract convexity spaces, which are separable. So we didn't use much about the geometry. And let me just read quickly. So an abstract convexity set is just a set system that contains the whole set. It's an empty set and is closed under intersection. Abstract convexity set. And it's called separable if there is the analog of a hyperplane, namely for any two disjoint sets S and T, there exists a separating half space where a half space is by definition a set in the collection so that its complement is also the collection. In the half space, also the complement is convex. And then basically everything that I said works for these abstract convexity spaces. So you can define the Radon number, and then there would be some results that if you know the Radon number, then the Tverberg number will satisfy the same type of inequalities that we've seen before. Essentially, we said this. So this is what is written here. So crucial, and this is related to some question of Ekhoff about the relation between the Radon number and the Tverberg number of abstract convexity spaces. So the original question was if they are related to each other, like we know by Tverberg theorem for the geometric case, and this is known not to be true. So there was some example by Boris Buch, and still you can ask what is the correct behavior, and the proof that I described here would give some bound which is better than some other known bounds, but let's not worry about this at the moment. So that's to you can see this thing here. I wrote yet another question here. So in Radon theorem and Tverberg theorem, we have completely precise bounds. And you may want to get completely precise bounds here. I don't have any good guesses, but at least maybe in the plane. So let me show you some example in the plane. So in the plane, if you want many points that still do not have a partition that cannot be separated by s-convex sets, and one example would be to take something like some convex polytope polygon, and replace the edges by concave things like this, but each of them maybe has to be pretty close to the edge of the polygon and now just put many points on each of them, like S points on each of them. And then you can convince yourself that even if the polytope has about S edges, so this is really essentially the example from the 10 et al. Paper, then we would be able to separate them. I mean, then for any partition of this into red and blue.
Is it an S-convex set?
What?
Now it's coming to the end.
Is it an S-convex set?
So this is
This is
just an example that you cannot partition into two. Whenever you partition it into two disjoint sets, we will be able to cover them by s-convex sets, each of them, and they will be disjoint. So if I have the red points and the blue points, or white points in this picture, then what we can do is that for the red s-convex sets, we will take just one from each edge like this, and we'll look at the convex hull, and we'll do the same for each set that contains at most one red point from each arc, and then the blue sets would be the convex hulls of the set of points in each edge here, right? So something like this maybe could give the exact truth for the plane. Didn't think about it too much, but maybe. In high dimension, it looks more complicated, but let's say maybe interesting. And there are maybe some other questions, but let's just finish here, and thank you for your patience of staying here 10 minutes over time.